Hello and welcome everyone. Now we'll discuss about the part C, data pre-processing for feedback analytics. Here data solutions and explanations are given, data pre-processing and normalization. So question number 9, we have the data quality issues in feedback analytics. Discuss data quality issues, accuracy, completeness and consistency in feedback analytics. Proposing two other dimensions of data quality relevant to learning analytics. So first is accuracy. Okay, data reflect the true state of feedback. Issue, contradicting ratings. Example, student rated a faculty member 5 by 5 for knowledge but 1 out of 5 for teaching style. So these both of the ratings are contradictory to each other. Okay, now impact, leads to misleading features, vectors and poor model training. Okay, then we have completeness, all necessary data is present. Issue, missing survey responses. Example, a student fills only half of the questions. Impact, reduces statistical power and requires imputation, which introduces bias. Okay, now we have consistency, data is uniform across the data set. Issue, inconsistent rating scales. Example, one department uses 1 to 5, another uses 1 to 10, or uses text labels like high or low. Impact, prevent direct comparison and aggregation of data without standardization. Okay, now we have additional dimensions for learning analytics. Timeliness, feedback must be recent enough to be relevant. Example, feedback from a course 5 years ago is less relevant than last semester's. Validity, data measures what it is intended to measure. Example, ensuring a course rating truly captures course quality and not the student's mood. Okay, now question number 10, handling missing feedback values. Discuss approaches for handling missing student feedback values. Example, constant, mean or median, mode imputation, class specific imputation or most probable values. Okay, now we have constant imputation, fill missing values with a designated constant, 0 or a value outside the typical range like -1. Use case, when missing itself as a feature. Example, did not answer means indifference. Okay, then mean mode imputation, replace missing numeric values with the column mean or nominal values with the mode. Okay, now what's the use case? So simplest pass and maintains the overall mean mode of the attribute. Now what's the caution that we have to take? Reduces variance and introduces bias if missing data is not missing at random MAR. Okay, now class specific imputation. So impute based on the mean or mode of the specific class or group of the student belongs to. Example, mean rating from student is the same department or year. Now what's the use case of it? So it exploits domain knowledge, more accurate than global imputation as it uses local characteristics. Now we have most probable values imputation. Example, using regression or KNN. Use a predictive model like linear regression or K nearest neighbors to estimate the missing value based on the other complete attributes in the profile. Now what's the use case? So its use case is high accuracy, preserves covariance, structure better than simpler methods. And what is the caution we have to take? And that is computationally expensive and complex. Okay, now question number 11 we are going to see. Now here the feedback rating, smoothing and outlier detection we have to do. So we are doing this with bin mean smoothing depth 3. Okay, so we have data. Question number 2, here the data is listed, we have to sort it. However, here it is we have to sort this. It's not sorted already. It's already sorted. Determine bin depth and size. So we have to determine the depth. Total values n equal to 22, number of bins 22 by 3 upon which is equal to 8. Okay, now partition into bins, size 3 or less, bin 1, bin 2, bin 3, bin 4. We have to calculate bin for each value. Okay, now bin, no remaining values. If we assume only the first 21 values, we'd have 7 bin exactly, but 22 values means 8 bins if the last bin size is size 1. Let's assume the list size of 22 is correct. If the list had 21 values, example stopping at 52, the 7 bins would be full. Giving the original data from Q2 has 2 values. The bins are as shown below. Again we have to the calculated values, we have here smooth the data, that is we have replaced bin values with mean. Okay, now suggest ways to detect outliers. So how can we do the outlier detection? So we have box plot, IQR method, description, calculate the interquartile range. IQR, you have to calculate Q3 minus Q1, values falling as outside the fences, lower Q1 minus 1.5 IQR and upper equal to Q3 plus 1.5 IQR are flagged as outliers. Use case, simple, effective for univariate data. univariate data, and robust to extreme values. Okay, then we have z-score method. Normalize data using the z-score formula. Z equal to x minus mu upon sigma. Any data point with a mod z greater than threshold, typically 2.5 or 3, is an outlier. Okay, now what's the use case? Effective if the data is approximately normally distributed, less robust if the distribution is skewed. Okay, now isolation, forest or local outlier factor. Description, machine learning techniques that identify points that are isolated from the rest of the data, isolation forest, or that have significantly lower density than their neighbors, LOF. Okay, now what's the use case? It's ideal for multivariate data and complex distributions where simple statistical rules fail. Okay, now point C, discuss other methods for data smoothing. So we have to discuss methods for data smoothing. So we have bin boundary smoothing. In each bin, replace all values with the closest bound array, min or max values of that bin. Bin median smoothing, replace all values in a bin with the median value of the bin, more robust to outliers than bin mean smoothing. Regression or curve fitting, use linear or polynomial regression to fit the data. The smooth value is the value predicted by the fitted line or curve. This helps identify trends and remove random noise. Okay, now moving average, replace each data point with the average of itself and its neighbors with a defined window, example a 3-point moving average. Okay, now question number 12 we have. So question number 12 asks for in data integration for MCM tech analytics, discuss schema integration, handling redundant data, example duplicate entries from multiple surveys and resolving conflicts in value. Okay, so first solution is schema integration, the process of combining schemas from multiple data sources into a coherent global schema. Issue, entity identification problem, example faculty ID in one system is instructor code in another. Resolution, use metadata matching, entity resolution techniques and data dictionary alignment to map equivalent attributes and resolve homonyms, same name but different meaning, and synonyms, different names same meaning. Handling redundant data, duplicate data that can be derived from the data. Issue, duplicate entries, example the same student submit feedback twice, or a course ID is stored both as course ID and course key. Resolution, perform correlation analysis to identify derivable attributes, use tuple comparison to find duplicate records. Prioritize one source as the master or compute an average consensus value. Okay, now resolving conflicts in value, discrepancies in attribute values across different sources for the same entry. Issue, contradictory feedback, example survey A rate faculty at 4 out of 5 but survey B rates them 2 out of 5 for the same period. Resolution, use consensus method, example average weighted average based on source reliability, or use time stamping to prioritize the most recent data. Now question number 13, 14 and 15 we'll discuss about normalization methods and calculations. So we have normalization methods as min-max normalization, z-score normalization, z-score normalization using mean, absolute deviation and decimal scaling. Okay, so min-max normalization rescales data to a specific range, typically 0, 1. Then we have the formula. Then z-score normalization, standard deviation standardizes data to have a mean of 0 and a standard deviation of 1. Then we have the formula of it too. Now z-score normalization, mean absolute deviation, MAD, less sensitive to outliers than using the standard deviation. Then we have the formula for this too. Okay, you can read the formula directly. Okay, now decimal scaling normalizes by moving the decimal point based on the maximum absolute value. Okay, now we have the formula for this as well. Now we have question number 14 and it has given us a data workload hours per semester, and what we have to do, we have to first do the min max normalization. For min max normalization we'll put the formula for each value and we'll get this table. Okay, then z-score normalization, standard deviation. In z-score normalization, this is the formula, that is sigma of a equal to 1 by 5 under root summation of vi minus 500 ka whole square. Okay, now we'll put values in it and we'll get the data. Now z-score normalization, mean deviation, absolute deviation, again the formula for this is MAD equal to 1 by 5 summation of vi minus 500 under modulus. Okay, and then again we have a table. Then decimal scaling. Decimal scaling means what? Max. First we'll take out the max of v, find the smallest j such that such as 1000, that is max of v upon min of v is less than 1, j equal to 4. 1000 by 10 by 4 equal to 0.1, less than 1, so j equal to 4 point v dash equal to v upon 10,000. Okay, and again it will give us a table. Now normalize feedback rating tables. Values. Feedback rating values 1 to 5 range, 1, 3, 5, 5, 5 using A to D. Data B. Again we have some data here, and now we'll do the min max normalization. So the calculated values should be presented over here. Z score normalization also here, and Z score normalization MAD, we have to do it by the formula, and then we have to present it in this kind of table. And then decimal scaling, again we'll put the formula and put it into a table. Okay, now question number 15 asks us to discuss which method is most appropriate and why. Most appropriate method is min max normalization. Reason: feedback ratings inherently use a bound linear scale 1 to 5. Min max preserves the relationship between the original values while scaling them to a uniform, easily interpretable range like 0, 1 or 0, 10. This is crucial because a rating of 5 is always the maximum possible satisfaction. Why others are less suitable? So Z-score methods B and C lose the boundary information. A Z-score can be arbitrarily large or small, which is meaningless for rating scale that cannot exceed 5. Decimal scaling D results in a narrow range of values 0.1 to 0.5, which offers low differentiation of a model. Now again we have given a question that is based on age and productivity normalization. We have given age A data where n equal to 18 and productivity data where also n equal to 18. Now to simplify calculations for a document, we will assume the provided means mu and the standard deviation sigma values from question 4th of the solution provided. Okay, so from there we are taking the values. Okay, now we have the formula v dash a equal to age minus 44.83 upon 12.94, and again we will tabulate these values. Then productivity normalization, we have the formula v dash p equal to productivity minus 30.65 upon 10.66, and again we will put them into this particular table. Now question number 17 is based on Pearson's correlation and covariance. Okay, so now firstly we have to compute Pearson's correlation, coefficient and covariance on the student project evaluation scores, and we have the evaluation scores here. Comment on whether the relationship is positive or negative. So correlation covariance requires two variables. The question provides only one set of scores x, that is having a set assumption. Since only one variable is given, a correlation or covariance calculation is impossible. The question likely intended to ask for the 5-number summary or mode median standard deviation similar to question 4 to characterize the single distribution. If the intent was to characterize the distribution of x, data x equal to 12, mean mu of x is equal to 747 upon 12, median 35 plus 50 upon 2, and standard deviation sigma of x equal to approximately 77.8. If the question intends to imply correlation with an implicit second variable y, example student ID or time, assuming y is the rank or index of 1 to 12 of the scores, x score we have the data here, and y rank we have the data here. Covariance means the joint variability of two variables. This is the formula for covariance. Since the scores in X are monotonically increasing except for minor differences, the scores increase with rank Y. Therefore, the product of the deviations will generally be positive, leading to a positive covariance. Okay. Now, Pearson's correlation coefficient R measures the linear relationship strength and direction Rx, y equal to covariant of x, y upon sigma x, sigma y. Since the values are presented in ascending order, there is a strong perfect relationship with the rank, resulting in a high positive correlation close to +1. Comment on relationship. The relationship is positive. Higher score values are associated with the higher rank in the list. Okay. Now question number 18, which is the last question of today. Techniques for feedback analysis. Uses a flowchart to summarize the attribute section. Techniques for feedback analysis. First we have forward selection. Start with an empty set of features. Repeatedly add the feature that provides the greatest improvement in model performance until no further improvement is observed. Heuristic greedy approach, highly efficient but may miss feature combinations. Backward elimination, process starts with the full set of features, repeatedly remove the feature that contributes the least to model performance until removal significantly harms the performance. Heuristic, exhaustive search can be computationally expensive but more robust than forward selection. Then hybrid method, process combines forward selection and backward elimination. Features are added one by one, but at each step, a check is performed to see if any previously added features are now redundant and can be eliminated. Heuristic balances efficiency and accuracy, often leading to better results than pure forward or backward methods. Okay, so that's it for today. Thank you for watching.